Now we discuss on how we can use this epsilon regularity to find the subgraph H in a given graph G. So recall that we defined this graph embedding. So we say that this map that maps the vertex of H to vertices of G is a graph embedding. If it is injective homomorphism. And all the edges map to edges. For all edges in H, its image is also an edge. So it's same as finding a subgraph, which is isomorphic to H. So you just see the image of this I, then that's a subgraph of G, which is, which contains H. So the following lemma, its name is embedding lemma. It's saying that for given epsilon regular partition, you can find the copy of H in there, appropriate copy of H in there. Let's say you have epsilon, which is sufficiently smaller than D and say 1 over delta. So this delta, before I said that most of the time the Greek letter is a number smaller than 1 and the English letter is integer, but this case it's not. It's an integer. This is a real number smaller than or equal to 1. But here, now say that suppose we have a partition of the vertex set of G and its Vi has size n. And its Vi Vj is epsilon d plus regular. Epsilon regular with density LSD for all I and j, distinct I and j. And let's say you consider H, let H be on alpha type graph with partition x1 to xr with maximum degree and most delta, and each xi is and most epsilon n. So what? In G you have this graph, and then in H you have this graph where you have x1, x2, x3, b1, b2, b3, and H has bounded degree, and then G is dense graph. It has quadratically many edges. H has only linearly many edges. Each xi is much smaller than di. Then you can embed this. You can find a copy of H in G. Then there exists embedding I of H into G with the image of xi lies inside of VR. You can put this into here, into here, into here, so that all the edges are mapped to edges. So how do we prove this? For each vertex, our strategy is as follows. You embed this one by one. You map it one by one. And once you map this vertex, there are no restrictions. You can map it anywhere. So this has candidate set, and this has candidate set. This has candidate set. Each vertex has candidate set where it can be mapped. And what you do is let's say you decide to embed here. Now that candidate set change. For this vertex, you cannot map it to the same vertex. So candidate set shrink by 1. So one vertex decrease. But for this vertex, let's say they were adjacent. Then now it has to be mapped into a neighborhood of this vertex. So you consider this neighborhood, and then this vertex, its candidate set shrink. On the other hand, if this is not adjacent to this vertex, then this still have the same candidate set. And you keep embed this, and next time when you embed it, now you embed into this candidate set, and then its neighborhood also its candidate set shrink. And then we measure how much it shrink and how many times it shrink. Every time its neighbor is embedded, it shrink. So the number of shrinking is small, M delta. And every time when you embed this candidate set shrink according to its degree of this vertex. So if we choose this vertex well, and you can make sure that this candidate set does not decrease too much. That's related to degree of this vertex. So this lemma is relevant. You can choose a vertex with the right degree so that you can control how fast it shrinks each time. So that's the rough idea. And you show that the candidate that never shrink too much so that you always have a option until you finish. Let's say you order the vertices x1 to xh with the vertices of h, and let's say psi I be the index such that this xi belong to capital X of psi r. So as I mentioned, we will construct an embedding pi by selecting its images, B1, which is image of x1, B2, which is image of x2, etc., one by one. And let's say we denote capital C sub I of j to be the set of all possible candidates. Of this Pj. After we determined B1 to Bi minus 1. So at the time of embedding I, Bi, where can Bj go to? So initially, we let the C1 of J be just entire B psi J. So because its Bj is in X psi J, so we want to map it into B psi J. And assume that we have determined B1 to Bi minus 1. And we have that each candidate set assigns at least delta plus 1 times epsilon n. So this satisfied initially. Epsilon is sufficiently small, so this bound is much smaller than n. And initially this has size n, so this satisfied initially. And inductively, we assume that this is still true at this moment. Now what? Now, as I mentioned, when you chose where to embed this, we want to choose the vertex which sends the Racho edges to here, so that the other candidate set does not shrink too much. And let's consider what vertices that might be affected. So that should be the vertex which is not yet embedded, and then it's adjacent to the current vertex. So let's say A is the set Vj, set of the Vj, Xj, which is neighbor of this Xi in H, and this J is bigger than I, so that we haven't embedded yet. Let's say that's X of S1 to X of SP. Then what we know? So currently you have Xi that's embedded to V sub psi I, and it has some neighbor, say Xj prime, and you want to embed this into V psi j, V psi j prime. So you have this candidate set. Now what? You know that these are epsilon regular, and then these are epsilon regular. So since it's V sub psi I and V sub psi SL, or at any SL, this is epsilon d plus regular for all L between 1 and P. And the previous lemma, the lemma about these, so B prime is our current candidate set in V sub psi SL. The candidate set C sub I of SL. Then you can control the number of vertices in A, number of vertices in here, which has the correct degree to this part. The previous lemma implied that all but and most epsilon n vertices in current candidate set, it has some candidate set here, have at least t minus epsilon times CISL neighbors in CISL. Hence, you do that for all choice of S1 to SP. We know that at least in this candidate set, the P is at most delta, so P that times, so P times epsilon n. So delta times epsilon n is lower bound, at least epsilon n vertices. So this is at least epsilon n because we inductively assume that this SI is at least delta plus 1 times epsilon n. This many vertices in Ci of I has at least d minus epsilon times Ci SL neighbors in each candidate set for all L. Also among them, at most epsilon n minus 1, so which is the size of this, the number of vertices in X sub psi I, except this pi. I mean, that's the maximum number of already embedded vertices in X sub psi I. So what? out of this candidate set, at most this many was not good, and most this many was already embedded. So you have still at least one choice. Thus, we can choose that as PI, which has at least E minus epsilon times CISL labels in CISL for all L between 1 and P. Then we update this PI to be the image of this sound. After choosing PI, we update Ci plus 1j. For all other j, you update this. If this xj is the neighbor of this xi, then you shrink. Otherwise, you keep it. So there was, as I mentioned before, that I mentioned that if you embed it, then there is another vertex. Its candidate set should shrink by one vertex by deleting one vertex. But in this definition, we don't work it that way. We just simply exclude the choice later, so they are still kept in the candidate set. So in terms of this candidate set, it only have two cases. Either it's same or shrink. And injectivity is ensured later when we make a choice. So this will shrink Cij by the vector larger than or equal to t minus epsilon. But we know that if xj has at most delta neighbors, thus the Cij has at least t minus epsilon to the delta n, which is at least delta plus 1 epsilon n for any case. Thus, this inductive hypothesis still satisfied. So, thus, we can repeat this and then we choose Vi as long as its I is at most age. We can simply repeat this. We can select P1 to PH and this resulting pi is what we desire, the embedding. Okay, and this embedding lemma is useful in many cases. And one is that we can use this to prove Ehrlich-Simonovich theorem in an easy way. How? So what's this is that if the number of edges is bigger than 1 minus 1 over r minus 1 plus delta n squared over 2 and h is r-partite, then H is in G. N is large. And epsilon is positive number. So let's say for this given delta, we choose epsilon, which is sufficiently smaller than delta. And we have this case. So for given delta in here, we choose epsilon, which is sufficiently small, but the n is still sufficiently large. Then what? If we have, let's not use R here. So it's confusing with the number of parts in regularity. So this is K-partite. And what? We apply regularity lemma to G, which say T being 1 over epsilon. Then we obtain, so this is to ensure that the number of parts in this regularity partition is not too small. We obtain an epsilon regular partition B1 to BR. Of G. And let R be epsilon, say delta over 3, say delta over 4. Reduced graph for this epsilon regular partition. And what we know is that this proposition that we didn't prove but introduced before, the reduced graph inherits the average degree. Okay, to be more precise, if you have a lower bound on the average object, then reduced graph almost inherits that lower bound. It could have a higher average degree, but the average degree does not decrease too much. Then by the proposition, we have that using this average degree, we can find the lower bound on this number of edges in R. You can prove this. So using that delta and epsilon are much smaller, and then R is big, so 1 over R is also much smaller than delta. The how much you lower is, you can bound this, then you get this. Then what do you know? We already know Turan theorem regarding this clique. This Turan theorem implies that this R contains a copy of complete graph on K vertices. And without loss of generality, we re-index the vertex set of this partition. We assume that the first K vertices in this reduced graph induces the complete graph. Then that means B1 and BJ, B1 and B2 are epsilon delta regular. I mean epsilon delta over 4 plus regular for all of them. Then what? As we assume this, and okay, technically here you have to also write 1 over K. So then you can now apply this embedding lemma to this part B1 to Bk. And in this Edison and Simonovich theorem, we assume n is large and then k is fixed, so that each xi size is much more than vi. So by using the embedding lemma, we can find a copy of h in G, specifically inside this part V1 to Bk. So this essentially shows that if you have a k-part type graph, then finding such a graph in G is just as difficult as finding a copy of kk up to small order term rule. Anyway, so this gives you an idea that why finding H is just as difficult as finding a copy of kk. Because as long as you find a copy of kk in reduced graph, then embedding lemma allows you to find any reasonable k-part type graph in your original graph G. And then while you're converting the original graph to R, the number of edges, the decrement of the number of edges is not big. So essentially, finding such a copy in G and R are almost equivalent. And in R, you only have to find kk instead of the k-part type graph H. Okay, so yeah, this is the embedding lemma that we have proved, and we use it to prove the Edison-Simonovich theorem. So that shows an application of this. And next natural question is that, okay, we can find a copy of H in G. Then how many can you find? Can you find actually many of them? So that we will discuss in the next video. And then we will see some variation of such a question and application of those. Okay, then thank you for listening. I will see you in next video.